Hello everyone, this is Amy. In today's video series, we will talk about a generalized version of Heisenberg's uncertainty principle. The original principle is about a particle's position and momentum, but in its generalized version, it can be applied to any two physical observables in matrix form. Also, in this series, we won't assume any prior knowledge, so first we'll go through the basics of quantum mechanics. Firstly, quantum states are represented by state vectors. Vectors are mathematical objects with a magnitude and direction. There are two types of state vectors, Bragg vectors and ket vectors. They are roll vectors and column vectors respectively. Let's see how they look like. Just like this. This is a Bragg vector and its corresponding ket vector. You may have noticed a conjugate sign for every component of the Bragg vector. So where does it come from? That is because state vectors are generally in a complex Hilbert space. Their components can be complex. When we convert a Bragg vector into its corresponding ket vector, we will need to transpose the vector and get the conjugate of every component of the Bragg vector, and so as the ket vectors of Bragg vectors. A Bragg vector and a ket vector can form an inner product. Let's see how it looks like. A Bragg vector and a ket vector form a bracket, as you can see here. So how do we calculate the inner product? We naturally just pick the corresponding components of the vectors and then multiply the scalars and sum them together. Let's look closer to this equation. Terms such as psi1 conjugate psi1 actually has some physical meanings. They mean the probability to get a certain value for a measurement. That's why the state vectors can actually represent some states such as superpositions. To know more about the relations of multiple state vectors, we shall take some examples. So as you can see, there are three vectors in the space, A, B, and psi. Obviously, the vectors A and B are orthogonal. In other words, they are perpendicular, but the term orthogonal seems more accurate because that means their inner product is zero. We can actually say they form an orthonormal basis for the state vectors right here. So what is meant by the term basis? That means the state vectors can be expressed as a term as a linear combination of the two vectors, such like this. This is a linear combination of A and B. Here is how we describe the quantum states psi. As you can see, 1 over square root 2 is the component of the state vector right here. I will leave a question for you. How can you write a component of the state vector in the form of the corresponding basis vector and the vector itself? Maybe you will say that it's cosine the angle between the two vectors, but that only holds for the real case. We're dealing with a complex Hilbert space. A more general concept to work with is the inner product, as we have mentioned before. But this time, it is an inner product between two different vectors, like this. This is the component of an arbitrary state vector, and E underscore m is the corresponding basis vector. Psi is the vector itself. One important thing to note here is that if we swap the two vectors right here, we need to add a conjugate sign for the component. So we use vectors to represent quantum states. What about physical observables? In quantum mechanics, physical observables are represented by Hermitian matrices. What is a Hermitian matrix? A Hermitian matrix is defined as this equation. It's defined as this. H equals to H dagger, where the dagger here means transpose conjugate. This is the idea we have explored before. We just transpose the matrix and then get the conjugate of every entry, and we find that it is actually completely equal to the original one. Then we say that this is a Hermitian matrix. You may be asking the question, how can even a matrix represent a physical observable? Actually, matrices have a lot of properties, and two of them is eigenvalues and eigenvectors. As you can see here, the scalar lambda here is the eigenvalue of the matrix, and the vector lambda is the eigenvector of the matrix. One eigenvalue can only correspond to one eigenvector, it can correspond to more eigenvectors. And the number of sets of eigenvalues and eigenvectors actually depends on the size of the matrix itself. So what are the physical meanings of eigenvalues and eigenvectors for Hermitian matrices? They are: eigenvalues are possible outcomes of a measurement, and eigenvectors are a set of orthonormal bases for an arbitrary state vector. The idea of eigenvalues is pretty clear right here, but eigenvectors, a set of orthonormal bases, what does it mean? That means the basis is orthogonal and normalized. They form a basis for a state vector to live in. So why do we specifically choose Hermitian matrices to represent physical observables? According to our definitions, we can finally explore the properties of this kind of matrices. The first property is right here. Hermitian matrices' eigenvalues are all real. Why is it important? Also, it's pretty clear. The outputs of measurements must be real numbers. Let's prove the property. Let's start with the definition of eigenvalues and eigenvectors. Then we convert the ket vectors into bra vectors, just like this. Notice we have added a conjugate sign for each side of the equation. We can actually remove the conjugate sign for the matrix H, because H equals to H dagger. Then we get this equation. Then we see some similarities between the two equations. That's why we multiply a bra vector and above equation and we get this equation. And then we multiply a ket vector for the equation below. Then we subtract the two equations. What we get is lambda equals to lambda conjugate. In other words, lambda must be a real number to let the definitions of Hermitian matrices hold. The second property of Hermitian matrices is that the eigenvectors of a Hermitian matrix form an orthonormal basis. Let's again prove the property. At first you can try it by yourself, because the proof is very similar to the first one. Again, starting with the definition of eigenvalues and eigenvectors. For the first equation, we convert ket vectors into bra vectors. Again, we multiply ket vectors and bra vectors respectively to the two equations. If the scalars lambda1 and lambda2 are not equal, then the inner product of lambda1 and lambda2 as vectors must be 0. For now, we have proved the property. So here's a question. What if we get a set of linearly independent state vectors in a space and we want to let it form an orthonormal basis? What can we do to them? Actually, we can use the Grmet process. What is the process about? The process is about transforming a set of linearly independent vectors into an orthonormal basis. Let's visualize it. The process is pretty simple. We're getting the three linearly independent vectors. First, we normalize the vector v1 as a start. We just preserve the direction of the vector while we make the magnitude to be 1. Then we project the second state vector to the first state vector, and then subtract it from the original one. Obviously, u2, this vector, is orthogonal to the vector u1. The second step is pretty simple. We just, again, normalize the vector. For the third vector, we need to project it onto the two vectors here, just like this, and subtract them to get a vector that is orthogonal to both the two vectors. Again, normalize the vector. Here is what we get, a set of orthonormal bases that spans a space. This is how we actually write the process. This process can be easily extended to higher dimensions, and therefore useful in quantum mechanics. Thanks for watching this video. For the notes and problems to work with, you can click the link in the description.